In this video, we are looking at stationary points. Stationary points are points where the gradient is 0. And we can have a minimum, a local minimum, a maximum, a local maximum, or a point of inflection. So 3 different types of points, stationary points, where the gradient is equal to 0. If you look at the gradient before and after the minimum, we've got a negative gradient before, a positive gradient after. So for a minimum, the gradient is going from negative to positive. So it's negative before, it's positive after, and we can see that the gradient is increasing. So the gradient of the gradient, our second derivative, will be positive. So a minimum, we go from a negative gradient to a positive gradient, and our second derivative, it's increasing, it's going up. So the gradient's going from negative to positive, so it's going up. At a local maximum, we have a positive gradient before the maximum and a negative gradient after the maximum. So we have a positive before, a negative after, and if it's going from positive to negative, what's happening to the gradient? The gradient is decreasing. So our second derivative is less than 0. The gradient of the gradient is going down. It's going from positive to negative. Therefore, it's going down. At a point of inflection, in this example, we've got positive before and positive after. We could also have negative before and negative after if it was the other way around. If it was like this. So we could have negative before and negative after. So it's the same, the gradient is positive and positive, or negative and negative, before and after a point of inflection. At a point of inflection, the second derivative is equal to 0, but having a second derivative of 0 doesn't mean it's a point of inflection, because it could be a point of inflection or a maximum or a minimum. And an example of that is y equals x to the power of 4. We've got a minimum point, but the second derivative is equal to 0. So if we've got a second derivative of 0, we don't know whether it is a point of inflection, a maximum, or a minimum. The reason we're calling them local minimum and local maximum, so this is the biggest point, the highest point locally. It's not the highest point on the graph. It's not the maximum, because the graph continues up here. So there are higher points. It's just the highest point locally. It's a local maximum. So we need to find the coordinates of the stationary points. The stationary points are where the gradient equals 0. So to do that, we're going to find the gradient function, dy dx. So dy dx. So times by the power, take 1 off the power. So 6x squared minus 1x minus 1. So that's our gradient function. The stationary points are where the gradient equals 0. So we've got 6x squared minus x minus 1 equals 0. How can we solve it? We could use the calculator, or we could factorize. Let's use the calculator. So menu, equation or function, polynomial, degree 2, so 6x squared minus 1x minus 1. So we've got 1/2 and minus 1/3. So x is equal to 1/2, x is equal to minus 1/3. We wanted the coordinates, so we need the y coordinates as well. So to get those, we have to substitute in x into our equation. So we've got 2 times 1/2 cubed minus 1/2 times a half squared minus a half plus 3. So that's 21 over 8. So we've got 1 half 21 over 8 and minus a third. I'm changing all of my 1 halves into minus a third. And we've got 173 over 54. So they are the coordinates of the stationary points. They are the points where the gradient equals 0. Now we need to establish whether they are the nature of them, whether it's a maximum point, whether each of them are maximums or minimums or a point of inflection. So to do that, we can either look at a point just either side. So we've got x is 0.5 here. If we looked at 0.4 and 0.6 and see what the gradient is either side. So if the gradient goes from negative to positive, it'll be a minimum. And if it goes from positive to negative, it'll be a maximum. Or we can find the second derivative, which I will do. So the gradient of the gradient. The gradient of the gradient is going to be 12x minus 1 times by the power, take 1 off the power. And then we'll look at whether the gradient of the gradient, the second derivative, is positive or negative. The gradient of the gradient, so when x is 1 half, 12 halves, take away 1, is 5. So for this point, when x is a half, the gradient of the gradient is positive. That means the gradient of the gradient is going up, and it's a minimum point. That's a local minimum. If the second derivative is positive, it's a minimum. And the other point, we've got 12 times minus a third, which is negative 4, take away 1. That's negative 5. The second derivative is negative, which makes it a maximum point. Here's one for you to try. Pause the video, give it a go. So find the coordinates of the stationary points again. The stationary points are where the gradient equals 0. The gradient function times by the power, take 1 off the power. The gradient function, we've got 3x squared minus 2x minus 8. We want to know where that is equal to 0. The stationary points are where that is equal to 0. So let's solve it by putting it into the calculator. So we've got 3x squared minus 2x's minus 8. So we have x is 2 and x is negative 4/3. We wanted the coordinates, so we're going to have to substitute in. So for 2, we've got 2 cubed minus 2 squared minus 8 2's plus 4, which is negative 8. So 2 negative 8. And for minus 4 over 3, we have 284 over 27. So they are the coordinates of the stationary points. We want to know what the nature of them is, whether they're maximums or minimums or points of inflection. So again, we could either look at a point just either side. So for 2, if we looked at 1.9 and 2.1, then we'll see what happens to the gradient either side. So if it goes from negative to positive, it'd be a minimum. Positive to negative, it'd be a maximum. And if the gradient stays the same either side, point of inflection. Or we can use the second derivative. So the gradient of the gradient, which is 6x minus 2. For x is 2. The second derivative is 6 2's take away 2, which is 10. So that's positive. Therefore, it's a minimum point. And for minus 4/3, six times minus 4/3 take away 2. So 6 times negative 4/3 is negative 8. Take away 2, negative 10. So that's negative. Therefore, that one is a maximum point. This one says, by considering the gradient on either side of the stationary point, show that this point is a point of inflection. So let's find the stationary point first. So the stationary point is where the gradient equals 0. So that's times by the power, take 1 off the power. 3/3 is 1, so we've just got x squared minus 2x minus 1. No, plus 1. So that is our gradient function. We want to know where it's equal to 0. So let's factorize this one. Again, we could use the calculator, but this is x minus 1 times x minus 1. There's only one answer. X is 1. We don't need to know the y coordinate. So the stationary point is when x equals 1. And we want to, by considering the gradient on either side of the stationary point, show that it's a point of inflection. So let's use x equals 0.9 and x equals 1.1. So we've got a point on either side of the stationary point. So if it's a point of inflection, the gradient will be the same on either side. So it's either going to be positive and positive, or negative and negative if it was going down. So let's substitute both of these into our gradient function. So we have 0.9 squared minus 2 0.9s plus 1. So that's 1/100th, 0.01. So dy dx equals 0.01. For 1.1, we have 0.01 again. So the gradient is positive on both sides. So dy dx is positive on both sides of the stationary point. Therefore, it is a point of inflection. One for you to try. Give it a go. So let's find the stationary point first. The stationary point is where the gradient is equal to 0. So dy dx, so times by the power, take one off the power, so 2x squared plus 12x plus 18. We want to know whether that's equal to 0. So 2x squared plus 12x plus 18 equals 0. We could use the calculator, but let's half it and factorize it. So it's x plus 3 times x plus 3. So again, there's only one answer. There's only one stationary point, and that's when x is negative 3. How can we show it's a point of inflection? So we're going to look either side of our stationary point. So we're going to use x is negative 2.9 and x is negative 3.1. We're going to look at the gradient for each of these 2 points. So if the gradient is the same both sides of the stationary point, then it is a point of inflection. So our gradient is 2x squared, so 2 times negative 2.9 squared plus 12 times negative 2.9 plus 18. So that's 1/50th, 0.02. So when x is negative 2.9, the gradient is 0.02. And when it's negative 3.1, it's 0.02 as well. So again, the gradient is positive on both sides of the stationary point. Therefore, it is a point of inflection.